Welcome to the deep dive. We're here to pull out the key ideas, the really surprising bits, and the essential context from some pretty complex source material.
And today we're diving into Max Planck. Everyone calls him the father of quantum physics, right?
Right, that's the title he gets.
But if you really look at the sources, the story is, well, it's more complicated. He's almost the reluctant revolutionary.
Reluctant? How so?
Well, the picture we get is of someone deeply conservative, scientifically speaking. He loved the idea of absolute laws, strict cause and effect.
Okay.
And yet, ironically, it was his desperate attempt to save that classical view, to keep it all neat and tidy, that forced him to introduce the quantum, the very idea that shattered the old order.
So we've gone through quite a bit, biographies, his research papers on black body radiation, even his philosophical writings.
Yeah, and they really show this paradox at the heart of his work. Our goal here is to unpack that and really get a handle on why his constant dollars is just so fundamental.
To get there, we need to go back a bit.
Yeah.
Late 19th century, right?
Exactly. The 1890s. You have to picture the scene. Physicists were feeling pretty smug.
Smug how? Like, job done.
Pretty much. Planck's own mentor apparently told him physics was basically a finished science. Maybe, a few loose ends, insignificant gaps to tidy up.
Huh. So Planck, trained in thermodynamics, searching for these absolute truths, he picks one of these minor gaps.
He did. And it turned out to be, well, not so minor.
Okay, so let's talk about that gap. The black body problem. What exactly was the issue they were wrestling with?
At its core, it sounds simple. It's just about why things glow when they get hot.
Like a hot poker or the filament in an old light bulb?
Precisely. Any object, just because it has a temperature, radiates energy, heat, light, electromagnetic waves. Physicists wanted one clean fundamental law to describe the spectrum of that energy, what wavelengths get emitted and how much of each.
They had the measurements, the experimental data?
They did, but the theories they had, based on classical physics, just didn't match up. Not across the board.
And this is where it gets messy for classical physics. The Rayleigh-Jeans law, based on all the established principles. What happened when they applied it?
Well, it worked okay for the long wavelengths, the low frequencies, think radio waves, infrared.
Yeah.
No problem there.
Right.
But when you got to the shorter wavelengths, higher frequencies, especially ultraviolet light, the theory went completely off the rails.
Oh, off the rails.
It predicted that a black body should emit an infinite amount of energy at those high frequencies.
Infinite energy? That's absurd. It makes no sense. A hot stove doesn't instantly vaporize the kitchen in a blast of UV light.
Exactly. It was a theoretical disaster. Later on, people famously called it the ultraviolet catastrophe. Classical physics was basically predicting nonsense.
So they were stuck. Was there anything else? Any other attempts?
There was Wien's formula. It was more of an empirical guess based on fitting the data.
Yeah.
And it actually worked quite well for the short wavelengths, the UV end.
Ah, so the opposite problem.
Right. Wien's law failed at the long wavelengths where Rayleigh-Jeans worked. You had two partial theories, neither covering the whole picture, and the fundamental one, Rayleigh-Jeans, led to infinity. Physics was genuinely stuck.
And this is the mess Planck steps into. But crucially, he wasn't thinking, I need a revolution. What was his actual goal?
Absolutely not revolution. His driving passion was thermodynamics, specifically the second law. He wanted to prove it was an absolute deterministic law, not just a statistical tendency like Ludwig Boltzmann was suggesting.
He didn't like Boltzmann's statistical approach, thinking about probabilities and atoms bouncing around.
Hated it. Planck wanted ironclad certainty, absolute causality. His initial goal was actually to derive Wien's law, the one that worked for short wavelengths, directly from the fundamental principles of thermodynamics and electromagnetism, to show it had to be that way.
So he was trying to use pure, absolute logic to derive a law that they already knew was flawed at the other end of the spectrum. That sounds precarious.
It was. And reality caught up with him fast. October 1900. That was the crunch time.
What happened in October 1900?
New experiments. Really precise measurements came out, and they showed definitively that Wien's law didn't just fail at long wavelengths, it failed quite clearly. The data was undeniable.
So the very law he was trying to derive from first principles was proven wrong by experiment.
Exactly. His whole theoretical project based on deriving Wien's law just collapsed. He couldn't rely on pure deduction anymore.
So faced with this contradictory data, what does he do? He needs something that matches the numbers.
Right. He has to pivot. He essentially says, okay, forget deriving it perfectly for now. Let me just find a mathematical formula almost like an educated guess, an interpolation that could just fit the data across the whole spectrum, something that bridges the gap between where Wien worked and where Rayleigh-Jeans should have worked.
And that mathematical guess, that becomes Planck's law.
That's it. He finds a formula that works beautifully, matches the experimental curves perfectly.
Okay, great. Formula found. But now he needs a reason why it works, doesn't he? A theoretical basis.
Yes. And this is the painful part for him. To give his successful formula a physical meaning, he was forced to turn to the very ideas he disliked Boltzmann's statistical methods, counting states, distributing energy.
The probabilistic stuff he resisted? That must have been tough.
You could say that. Sources say he called it an act of desperation. He had to figure out how to count the ways energy could be distributed among oscillators in the black body to make his formula emerge naturally.
And that counting process led him somewhere unexpected.
Completely. To make the statistics work out, to get his formula from the counting, he had to make what he termed a purely formal assumption. A mathematical trick, he thought.
Which was?
That energy wasn't a continuous flow. It couldn't be divided infinitely. Instead, it could only be emitted or absorbed in discrete chunks, indivisible packets. He called them quanta.
The birth of the quantum, just like that. An assumption to make the math fit.
Pretty much. And this led directly to that iconic equation. The energy, a corollary of one of these quanta, is directly proportional to its frequency.
1h equals nu. And there it is, the dollar. Planck's constant. What does that little h really mean for the universe?
It's profound. Dollar isn't just a conversion factor. It's sometimes called the quantum of action. It fundamentally represents the smallest possible step, the minimum unit of change that can occur in a physical interaction.
Smallest step size.
Yeah. Planck calculated its value, incredibly close to what we use today, around $6.06 times 10^40 years. The absolutely crucial point is that the dollar is not zero.
If it were zero,
Then energy would be continuous, classical physics would be perfectly fine, and there'd be no quantum mechanics. The fact that dollar is tiny but finite and non-zero is the physical proof that the universe, at its most fundamental level, is grainy, not smooth. It's discontinuous.
which is revolutionary. But the amazing thing is, Planck himself didn't seem to grasp the full implications at first, did he?
Not at all. He announced it in December 1900, but for years afterwards, he genuinely thought it was just a mathematical tool, a temporary fix. He actually spent time trying to figure out how to get rid of the quanta, how to absorb this discontinuity back into the smooth, classical framework.
He invented it but didn't quite believe it was real.
Exactly. He was deeply uncomfortable with its implications. The person who really saw the physical reality, the revolutionary core, was someone else.
Let me guess.
Einstein. Albert Einstein, yes.
Yeah.
5 years later, in 1905, his miracle year, he took Planck's idea and ran with it.
How did Einstein use it?
He used it to explain the photoelectric effect, how light shining on metal can knock electrons out. To make sense of that, Einstein made a truly bold leap.
Bolder than Planck's.
Much bolder, conceptually. Planck had quantized the process of energy emission and absorption. Einstein proposed that light itself is fundamentally made of these discrete energy packets, that light is these quanta, which we now call photons.
So not just the interaction, but the thing itself is quantized.
Yes. Einstein took Planck's mathematical necessity and declared it a physical reality. That really cemented the quantum idea.
And looking forward from there, this constant dollars ends up defining the absolute smallest scales of reality through the Planck units.
It does. It's amazing. If you combine dollars with the speed of light, c-hours, and Newton's gravitational constant dollars, ds, you can derive fundamental units of length, time, and mass.
The Planck length, Planck time.
Right. The Planck length is mind-bogglingly small, about 1035 meters. These units are thought to represent the scale where our current theories, quantum mechanics, and general relativity fundamentally break down. It's the boundary of known physics.
It's fascinating, then, that Planck, the originator of this quantum weirdness, later became one of its biggest critics philosophically. He and Einstein pushed back against the next generation.
They did. It's another layer of irony. Planck was actually a huge early supporter of Einstein's special relativity, helped bring him to Berlin. But later, both Planck and Einstein strongly objected to the so-called Copenhagen interpretation of quantum mechanics.
The one developed by Niels Bohr, Werner Heisenberg.
That's the one. And their objection wasn't just about the math, it was deeply philosophical. Copenhagen introduced fundamental uncertainty, randomness, probability right into the heart of physics. Delta X, delta P, X bar 2, and all that.
Which violated Planck's core belief in
strict causality, determinism, an objective reality governed by unbreakable laws. If quantum mechanics was inherently probabilistic, if you could only know the odds, not the exact outcome, well, that undermined everything Planck believed science was about.
So the very field he accidentally started ended up challenging his most fundamental view of the universe.
Precisely. He spent his life searching for absolute order, and his own discovery paved the way for a theory suggesting inherent randomness.
You mentioned his desire for order. It seems that wasn't just scientific, but a deep part of his personality, maybe something that helped him cope with, well, an incredible amount of personal tragedy later in life.
It's almost unbelievable when you list it out. He came from this highly cultured academic family. He was apparently a gifted musician, played piano, organ, even composed. He saw harmony and order in both music and physics.
But his personal life?
It was marked by devastating loss, especially after his scientific breakthrough.
What kinds of losses are we talking about?
First, his wife, Marie, died relatively young in 1909. Then World War I took his eldest son, Carl, killed in action in 1916.
Terrible.
And it didn't stop. His twin daughters, Marguerite and Emma, both died in childbirth, just 2 years apart, 1917 and 1919.
Oh my God, both twins.
Both twins dying the same way.
Right.
And then much later during World War II in 1944, an Allied bombing raid completely destroyed his house in Berlin. All his papers, his scientific journals, his correspondence, everything gone.
His entire life's work, the physical record of it.
Wiped out. And then the final, maybe the most horrific blow.
His other son.
His surviving son from his first marriage, Erwin. He was implicated in the 1944 plot to assassinate Hitler. He was arrested, tortured, and eventually executed by the Nazis in early 1945, just months before the war ended.
It's just an unimaginable sequence of tragedies. How does someone even continue after all that?
It speaks volumes about his resilience, his sense of duty, perhaps that inner core searching for order amidst chaos. And even during the Nazi era, he showed quiet courage.
How so? He wasn't overtly political, was he?
No, not a loud resistor, but he held on to his principles. Sources mention he actually went to see Hitler in 1933.
He met Hitler. Why?
To personally protest the firing of Jewish scientists, like Fritz Haber. It was apparently a tense meeting. Hitler flew into a rage. It achieved nothing practically, but Planck felt he had to make the stand.
That took guts, especially then.
It did, and his moral standing was recognized after the war. The Allies needed respected figures for rebuilding German science. They took the leading research organization, the Kaiser Wilhelm Society, and renamed it in his honor.
The Max Planck Society.
Exactly. It still exists today, a major research institution. Renaming it after him was his strategic move to lend his untarnished reputation and moral authority to post-war science in Germany.
So bringing it all together, his science accidentally started a revolution. He resisted. He endured immense personal suffering, yet maintained his moral compass. What about his final thoughts, his philosophy? Did he reconcile with the quantum world?
Philosophically, he never really gave up that search for an objective reality, governed by absolute laws. He saw science itself as requiring a kind of faith.
Faith? In what sense?
He wrote something quite striking. Anybody who has been seriously engaged in scientific work realizes that over the entrance to the gates of the Temple of Science are written the words, "Ye must have faith." Faith in the ability to understand, faith in the underlying order, perhaps.
But then he also said some things that sound, well, almost mystical, especially coming from a physicist.
Extremely surprising. Considering his life's work was about the fundamental constituents of matter, listen to this quote. "I regard consciousness as fundamental. I regard matter as derivative from consciousness."
Whoa! Consciousness first, matter second. From the guy who kicked off quantum physics.
It's a stunner. It almost flips the usual scientific materialism on its head. It suggests that maybe the observer isn't just passive.
And he had one final thought, summarizing his life's research on atoms.
Yes, equally profound. As a man who has devoted his whole life to the most clear-headed science, to the study of matter, I can tell you as a result of my research about atoms this much. There is no matter as such.
No matter as such? What do you mean? That it's all energy? Or action?
It seems he meant that the fundamental reality isn't little hard balls of stuff. It's more about the interactions, the processes, the quantum of action itself, represented by dollars. Matter emerges from that, perhaps even from consciousness observing that action.
So, Max Planck, the reluctant revolutionary, forced by data into an act of desperation that fundamentally changed our view of reality. He wins the Nobel Prize in 1918 for a discovery he wasn't even sure was real, while navigating incredible personal loss and historical turmoil.
It's an incredible story. A man seeking perfect order who ended up defining the granular, quantized nature of the universe.
And the questions he raised are still with us. His constant dollar defines that Planck scale, the very edge of our understanding where physics breaks down.
Right, where quantum effects and gravity must somehow merge into a theory we don't have yet.
So here's the final thought to leave you with. If Planck units mark the limit of physical reality as we know it, and Planck himself came to believe consciousness was fundamental and matter derivative, what does that combination imply? What role might consciousness play in the ultimate theory that finally unifies the quantum world and the cosmos?
His reluctant revolution, born from a crisis in classical physics, continues to push us right to the very edge of existence itself. What is reality at the Planck scale? We still don't know.